You know, something you don't see on the internet very often anymore now is people doing projects with PICs, the peripheral interface controller, by the company Microchip, true microchips. You see Arduinos, everyone uses an Arduino now, or a Raspberry Pi, but this is an actual PIC, that little chip down in there, little 8-pin dip chip. That's a PIC12F675. This is a tattoo power supply for someone, a friend of mine, texted me the other day asking if I could. I've built their current supply for them, but they've changed their setup a bit, asking if I'd be interested in, making them a new one. So whilst we're at it, I said we'll make it all as wireless as we can. So it's got a wireless. We'll make a wireless foot pedal for it and a remote controlled power supply. So this is the foot pedal side. This is a PIC12F508 running a little 433 meg RF transmitter, and it's, when you press it down, it will set the input pin low. It's pulled up high by a 470k resistor, so it only draws microamperes when it's being held down. It changes the input pins. The PIC wakes up, initiates the command. It senses whether the pin's gone high or low, and initiates the 16 bits or 17 bits of data transmission. Actually, it's not. It's a start bit, 16 bits and a stop bit, so it's 18 bits of data transmission. So it's got an on-off command. So see the LED there. Look, this is in on-off mode. So foot pedal down comes on, foot pedal up goes off. But she was on about last time I see her that she changed her setup because it was giving her a bad back, constantly holding her foot down on the foot pedal. So I've made it so if you press the button on the remote control, you can then put it in latching mode. So you press it down once, it goes on. You can let your foot off the foot pedal and you have to press it down again and it goes off. So that's latching mode, but I'm going to run that off an old CR2123 battery, and it'll last years because it draws nothing. It goes to sleep mode and draws, I can't measure the current. So it draws practically nothing in standby, and then a little burst of current on wake up. And even if she's got it in, if she's doing detailed work and has got it in on-off mode, it's microamperes of current going through that resistor whilst the foot pedal's held down. So there's that. But if the foot pedal does pack up, or she decides she doesn't even want to use the foot pedal, or kicks it out of the way and she's nearly finished a tattoo, she can actually just use, I've also programmed it so the button on the remote control will turn it on and off as well. So that's the foot pedal side. Power supply side, there's some functionality. So you got two lights here. So you can see that's a 7-segment display. That's actually just for me. I put that on there whilst I was checking the code was working correct to drive it all. There's actually going to be some Russian little glass vacuum tube looking vacuum fluorescent displays, and they need a heater voltage and stuff. So those two LEDs on the side there, that's shutdown mode. Power supply is going to have the main transformer in it, and then a very, very small transformer which is going to just supply enough current to keep the PIC running. So on wake up, press of any button will wake it up. Those two LEDs coming on, one of them is going to be sending a signal to the power supply, which is going to be on an umbilical somewhere else, the actual AC side of it, through an opto isolator to tell it to shut some relays in, initiate the main transformer, and also the standby transformer is going to have a resistor, I think, in series with it. So it's barely able to just hold the 5 volts needed to keep this ticking over. And it'll switch them in and allow full power through. It's got on a timeout function, so after a period of time it will shut off, or you can do it on remote if you want. Just power saving, it's 2023, we're all trying to be power conscious, so that's the shutdown process. So remote wise functionality, this is just a cheap eBay remote, but it kind of worked. I'd like to see if I can do something with these buttons, because that's the toggle setting, that's on off and that's shut down. So you can select your voltages 1 to 9 or 0 to 9, and then left to right gives it 0.5 increments, and up and down gives it 0.1 volt increments. So 5, the LEDs on the side are still outputting binary coded decimal, so you can see 5.1, 2, 3, and then if I hit a 0.5, that's 0.8, so that's an 8's lit up, that's 9, you see. And if I go next one round, it'll be a 4's lit up, and then 5 again, and so on. So the PIC12F675 has the RF transmitter and the IR receiver going straight into it. It's using the interrupt routine to see when the inputs change state. It's driving 2 shift registers. There's 2 8-bit serial shift registers here. The upper one, which takes the upper 16 bits, most significant bit first, that's going to be driving 2 binary coded decimal to 7 segment display drivers. So I've only got the one for the whole numbers actually connected. This one's showing the fractions, but you can see the binary coded decimal still outputting correctly. So instead of having to write routines and have lots of output pins to drive displays, just use the good old-fashioned 7 series logic binary coded decimal to display driver. So that's all 8 bits of the upper shift register. The lower shift register, its outputs control these 2 and the relay, which is going to latch the output. So when you press the pedal up down, it's just going to turn a relay on. So it's driving that, and it's also, and it's quite a, when you start doing the maths, it's quite a lot of data has to pass through. It also drives a 10-bit analog to digital, digital to analog converter. So you think about when you send a shift register data stream, it wants 8 bits. So you're all idle low, you send your data whether it's high or low, you then clock pulse high low, then your next data high low. So you have to do that 8 times. So you think you've got 8 clock pulses there and 8 data bits. Well, the DAC works in the same way. It has a data pin and a clock pin. So to get the data pin to change once, you have to clock all 8 bits into the shift register. I have to do 8 because I've got other things connected to it and I don't want to disturb them. So it clocks a full byte of data in. That changes the pin, whether the data pin's high or low. It then has to clock another full byte of data in, just to latch the clock pin high, and then another full byte to latch it low. It then has to do that 8 times to latch, 10 times to latch all 10 bits in, because it's a 10-bit DAC. And then has to do it twice more to latch in, just they're like, it doesn't care, but it's just the way it works. It needs to see 12 bits of data before you can latch it in. So you've clocked in 12 bits, but the last 2 I don't have to do data pin changes. It doesn't matter what state it's in. So you latch in 10 bits, you then just latch in 2 clock pulses. It saves a few cycles of this. And then the final one is you've got to latch another full byte in, and then that does the chip select pin or data latch, and then another byte just brings that low again on idle. So you can imagine actually quite a lot of data has to go through the shift register but it doesn't matter. It takes fractions of a second. And yeah, if I look at the multimeter, I've got it set on millivolts. I've just got this cranked down real low. It's got a adjustable analog reference on it, so just with the voltages I'm using, it was easier to put it on millivolt scale. It's going to be buffered by an op amp and stuff anyway with gain. So but yeah, if I select 1 volt, and you see it's instantaneous. You can't even see it. It's actually so those are whole volt. Remember, it's only a 10-bit register, so there is some, it is out slightly, and as obviously my pin's not set perfectly accurately, but yeah, so that's full volts. Then you see 0.1 volt increments, and then 0.5 volt increments. So yeah, and the highest it will go to is 9.9. You can see that's it, 9.9. So it's not far out. If we drop back to 1, you see I can go down to half a volt. You know, it's not a million miles out. It's certainly more of it's not a scientific piece of equipment. It's certainly more accurate enough for tattoo duty. So yeah, and it's all coded in assembly. None of that C malarkey. None of that processor exhaustive C. So I've just got to put one more routine into this. I've got to write the timing routine for the shutdown. I've got to be careful when I do that, because whilst it's picking up transmission of the IR or the RF signal, it's actually using the internal timer registers. It sees a pin change, it sees which pin it is, sees where it's gone high or low, and then decides from that whether to just go back to the main program loop, which is really just a few lines of code doing nothing, or whether to see how much time's passed. So for instance, this RF is idle low, so when it goes high, it clocks whatever's in the timers into the RAM storage. It's using timer 1, so it's got 2 RAM bytes. It clocks the data, the values of them into it, and then just goes back to the main program loop. When this goes low, it goes, well, it's gone low, I don't care about that. I only need to know how much time's passed when it goes high again. So when it goes high again, it sees how much time's passed, and it decides, it's looking for a start bit. Once it's got a start bit, it tells it it's seen a valid start bit, and then same again as data goes along. If the timing falls outside those areas, it just errors and returns to the main program and voids. It's a very similar thing with the IR remote. It just does it a bit quicker, and it's got start bit, stop bit, and 32 bits of data, but very similar process. So obviously, if I write a timing routine, I need to make sure I'm not messing about when it's trying to do timing. The last thing I want to do is accidentally mess up something that's stored in one of the internal timers, doing a 10-minute timeout or whatever on the shutdown side of things. So yeah, I've just got to make sure I don't mess anything up with that. Should be easy enough. But yeah, and to be honest, that you can get 1024 words of code. There's like 1024 program lines essentially you can put in the memory on that. It's 1024 bytes of memory essentially for program, and it's up to over 900 bytes now. So it's going to have nearly completely maxed out its internal memory with the program that's running all this. But yeah, anyway, so this is the incredibly messy, what the hell's going on wire breadboard setup. So next step, after I've just done that last little bit of programming, is to start making the circuit boards and then just make the case. So yeah, anyway, I'll film another video once I've got the boards made and testing that on the bench to make sure, because you guarantee you never make circuit boards first time around without making a mistake. So we'll see how that works out. And yeah, if you have watched this, as always, thanks for watching.